let's talk about one of the most important, yet completely invisible technologies that runs our world. This is the story of cryptography, the incredible art and science of keeping our digital lives secret.
I mean, just think about it for a second. Your bank account, that private message you just sent, our entire digital world is built on a foundation of secrecy. It's all powered by digital locks so mind-bogglingly complex, they make a physical padlock look like a toy.
So, here's the big question, the fundamental challenge of it all. We need to share information, right? But in a world where anyone could be listening in, how on earth do you do that safely? It's a puzzle that's captivated people for centuries, and it all boils down to one simple idea.
Now, the oldest and probably most obvious answer is something you've definitely heard of: encryption. But as we're about to see, this simple solution creates a really challenging puzzle of its own.
Okay, so the basic idea is super simple. Encryption just scrambles a readable message, what we call plain text, into a jumbled, unreadable mess called ciphertext. And the only way to unscramble it is with a secret key. You can think of it like this. Your message is a letter, and the ciphertext is that letter sealed inside a locked box. The key is the only thing that can possibly open it.
So this brings us to the first major approach, symmetric keys. Let's use the classic cryptography characters, Alice and Bob. Alice puts her message in a box, locks it with a unique key, and sends that box over to Bob. But for Bob to read it, she has to send him the exact same key. One key to lock it, the same key to unlock it. Simple, powerful, makes sense, right? Well, hang on a second. If they're talking over an insecure channel, like the internet, how does Alice get that secret key to Bob safely? If she just sends the key out in the open, an eavesdropper can just snatch it, and then you're right back to square one. This is the classic, frustrating key distribution problem. For a long time, this key problem seemed pretty much unsolvable. But then, back in the 1970s, a totally revolutionary idea came along that just flipped the entire puzzle on its head. And that's the magic of public keys. Okay, here's the breakthrough. So on the left, you've got the old way. One shared secret key does everything. But the new way, over on the right, uses a pair of keys that are mathematically linked. You have one public key for locking and a completely different private key for unlocking.
Imagine you create a special kind of padlock. That's your public key. You can make thousands of copies of this padlock and give them to literally everyone. Anybody can use one to lock a message in a box and send it to you. But, and here's the really crucial part, only you have the one-of-a-kind private key that can open that padlock. This is the absolute genius behind that little lock icon you see in your browser. It's what secures pretty much every website you visit.
All right, so we've solved the secrecy problem. But what about integrity? How can we be 100% sure that the message we get is the exact one that was sent, with nothing added, removed, or changed along the way? Well, for that, cryptography gives us what you can think of as digital fingerprints.
This is where another amazing tool comes into play, the hash function. A hash function is kind of like a wood chipper for data. You can feed anything into it, a single letter, a whole book, even a movie, and it spits out a unique, fixed-length string of characters. That's its digital fingerprint, and it acts as a perfect tamper-proof seal.
Let's see this in action with a really common hash algorithm, SHA-256. So if we feed it something incredibly simple, like the single letter A, look what it spits out, this long, complex, and totally unique string of characters. That's the fingerprint for A. Now, watch what happens if we change the input by just one tiny bit. We'll go from A to B. The output becomes completely, wildly different. It's totally unrecognizable. This is called the avalanche effect. Even the smallest, tiniest change creates a brand new fingerprint, which makes it instantly obvious if a file has been messed with in any way. Okay, so the systems we've just talked about, asymmetric keys for secrecy and hash functions for integrity, these are the absolute bedrock of modern digital security. But on the horizon, there's a storm brewing, one that threatens to shatter it all. And that is the coming quantum storm. So your computer, my computer, they think in bits. A simple on or off, a 0 or a 1. But quantum computers, they use what are called qubits. And a qubit can be a 0, a 1, or, thanks to the bizarre laws of quantum mechanics, it can be both at the exact same time. This wild ability, called superposition, means they can explore a huge number of possibilities all at once, giving them a level of computing power that's almost impossible to wrap your head around.
And that incredible power is a direct threat to us. As you can see here, the math behind our public key systems is extremely vulnerable. A quantum computer running something called Shor's algorithm could just shatter it. Now, symmetric keys and hash functions, they're much safer. Their security would be weakened, sure, but we could probably fix that just by making the keys longer. But that public key system that secures our entire internet, it is directly in the line of fire.
And look, this isn't science fiction. The threat is so real that way back in 2015, the NSA officially called for a transition to quantum-resistant algorithms. The global race was on to find a whole new generation of codes that could actually withstand a quantum attack. But here's the good news. Cryptographers are not just standing around waiting for this to happen. Which brings us to the final and most hopeful chapter of our story, the global race to build the next generation of truly unbreakable codes. All around the world, scientists are developing brand new types of public key systems. They're based on entirely different kinds of difficult math problems, things with cool names like lattice-based and code-based cryptography. The whole point is that they're designed from the ground up to be hard for any kind of computer to solve, whether it's classical or quantum.
But, this story never really ends. Cryptography has always been an arms race between the codemakers and the codebreakers. So as we build these new post-quantum systems, the big question is still out there. Are we finally building a truly unbreakable safe? Or are we just designing the next really complex lock that someday someone is going to figure out how to pick?